Hello students, welcome to my channel. Let us solve a problem from GATE 2004. Question number 81. This is a common question. A polyethylene film of 200 mm thickness is to be used for wrapping banana at 30 degree Celsius temperature. The partial pressure of oxygen outside and inside the wrapper are 21.3 kilopascal and 1.01 kilopascal respectively. The partial pressure of nitrogen outside and inside the wrapper are 78.02 and 1.01 kilopascal respectively. Permeability of oxygen and nitrogen at 30 degree Celsius temperature through polyethylene are 4.12 into 10 to the minus 16 meter cube per meter per second per kilopascal and 1.5 into 10 to the minus 14 meter cube solute per meter per second per kilopascal respectively. So, you have to calculate the flux of oxygen through polyethylene at steady state, and you have to find out the flux of nitrogen through polyethylene at steady state. So, basically there are two gases are there, oxygen and nitrogen. So, you have to find out the flux or the passing mass flow rate, you can say, or molar flow rate you have to calculate. So, let us first discuss about the theory of this problem. So, the answer of this question is very easy, but you need to know the theory, the mass diffusion theory actually. Let us study little about the theory. First of all, the gas transportation. So, gas transport through non-porous membrane, in this case this is a polyethylene membrane. So, this is not, which is not porous. So, which is actually governed by the Fick's law. You should know little about the Fick's law of diffusion. So, generally diffusing, so a law of diffusion. So, the generally J A is equal to d dCA divided by dx. So, where actually J is the molar flow rate or flux of the component A through the membrane. So, any membrane. So, let us see. So, the passing through the any gas from this side to this side. So, basically the concentration gradient, let it dCA by dx. So, x is the thickness of the membrane, let it be. So, therefore, d is the diffusion coefficient in this case. So, this is the molar flux rate or flow rate through the membrane. So, this is the Fick's law. Here actually the diffusion describes the movement of the gas inside the membrane and is a measure of the area of the membrane per time. So, basically under steady state condition, generally the Fick's law, integration of this Fick's law across the membrane relates the molar flux to the concentration which is given over the both side. Let it, the concentration of this side is Ca1, this is Ca2 or vice versa. That is Ca2, this is Ca1. So, more in this side and that is less is that side. So, therefore, the movement of the mass coming from this side to this side. So, therefore, we can write down the equation at steady state. J A will be equal to d. So, instead of dCA we can write down the concentration gradient, that is Ca2, concentration of one side minus concentration of the other side, divided by L. L is the, in this case x is L, L is the thickness of the membrane. So, the solubility coefficient in this case is a thermodynamic parameter, which is a measure of the gas absorbed by the membrane under the equilibrium condition. So, basically if you say this membrane is a very big one, so here actually there will be coming something like this. So, there will be equilibrium will be maintained inside the thickness of the membrane in this case. So, therefore, ideal system where the concentration are related to the partial pressure. So, since we are talking about the gas, so here the partial pressure comes. So, partial pressure of this side. So, let us this P A 2 this is partial pressure P A to small PA1. So therefore the Henry's law will be governed when the partial pressure comes into picture. So therefore, Henry's law says that the concentration is directly proportional to the solubility of that gas into the concentration, that is into partial pressure. Solubility into partial pressure, so is equal to the concentration of that gas. So according to the Henry's law. So there are two laws are there in this case. So where S is the solubility coefficient, so you can say solubility coefficient, and which is mole per meter cube per Pascal, you can say, and this is partial pressure of component which is has to be passed through the membrane. So component, let it A, therefore P A will be there. So which will be in Pascal or kilopascal, whatever there the unit. So in this case, in this problem, the kilopascal is there. So Pascal or kilopascal does not matter, and therefore using the gas law, our volumes is measured of amount of gas per volume of the pressure at a particular pressure, using the unit, let it meter cube per meter cube into Pascal, and here actually we will combine the Fick's law and Henry's law. So Fick's law and Henry's law, so you can say Henry's law we can just use, that is JA will be equal to D here instead of C, SPA 2 minus SPA1, you can write down, divided by L. So this is, since also we know that P, where P is the permeability of the gas. So permeability in the form of mole per meter per second. So you can say let permeability of gas, particular gas, let it A in this case, so which is equal to solubility into D or diffusibility. So S into D is permeability, you can say write down. So D is the diffusion and S is the solubility. Therefore it is a measure of amount of gas per unit area using the standard temperature and pressure, that is meter per meter square second Pascal. So in case A, the unit will be meter cube of solute per meter second Pascal, meter per second per Pascal. So this is the pressure, this is the unit of permeability or capital P, you can see in this case. So this is the formula. So now we can rewrite the formula, that is Na would be equal to, Na is the molar flux, that means kg mole flux per meter square per second. So we can write down, so that is Na will be equal to P is the permeability into partial pressure of A2 minus partial pressure of A1 divided by L. So this is the equation for the molar concentration, so flux. So since Na, you can say Na is flux at steady state in kg mole per meter square per second. Since we know the meter cube to kg mole, how to convert? So, the 1 kg mole is equal to 22.4 liter or 22.4 into 10 to the power minus 3 meter cube. So, this way we can convert the final formula will be Na in kg mole per meter square per second. So, that will be equal to permeability into partial pressure A2 minus partial pressure A1 divided by L into 22.4 into 10 to the power minus 3. So, here now coming to the question number 81, it is very simple. So, question number 80. So, here actually the data are given. First of all, it is asked to find out the oxygen flux, the flux of oxygen through the polyethylene in steady state. So, the things are given. Let it permeability first, PO for oxygen, that is given is 4.12 into 10 to the power minus 16 meter cube solute at STP per meter per second per kilopascal. So, this is given, and partial pressure, let it PO2 is given outside, inside and outside it is given. So, that is PO2, let it be 21.30 kilopascal, and partial pressure of 1. So, that is given as 1.013 kilopascal, so our atmospheric pressure, and the thickness of the polyethylene is given 200 millimeter. So, that is 0.2 meter. So, putting everything into this one, so therefore, NO will be equal to, so permeability is 4.12 into 10 to the power minus 16 into, so partial pressure is 21.30 minus 1.013 divided by 22.4 into 10 to the power minus 3 into 0.2. So, this is very simple. So, just putting the values together, so we can get the answer is 1.86 into 10 to the power minus 12 kg mole per meter square per second. So, this is the answer for question number 80. Now, coming to the question number 81. So, it is asked the flux of nitrogen through polyethylene at steady state, same thing. So, here the let it permeability first for nitrogen is given, that is 1.5 into 10 to the power minus 14 meter cube solute at STP per meter per second per kilopascal. So, it is given, again the partial pressure. So, for N2 is given the higher side, that is 78.02, and partial pressure of the lower side 1. So, that is given as 1.013 or atmospheric pressure. So, kilopascal. Now, putting the values, so you can find out the flux of nitrogen through the polyethylene, that will be N, so will be equal to 1.5 into 10 to the power minus 14. So, partial pressure, that is 78.02 minus 1.013 into divided by 22.4 into 10 to the power minus 3 into 0.2. So, that can be calculated, the value will be 2.58 into 10 to the power minus 10. So again the unit will be kg mole per meter square per second. So this is the answer for the question number 81. So the question number 80 is answer is 1.86 into 10 to the minus 12 mole per. So therefore the answer will be A. And question number 81, the answer will be D. So that is 2.58 into 10 to the power minus 10 kg mole per meter square per second. So hope you understand this problem. Please like and subscribe to my channel.